We'll wait for a couple of minutes for people to join. Let's wait another minute for people to join. Okay, let's get started. It's okay if people join a bit late. So, just as a quick recap, this is the live session for the week 2 of the Operating Systems Fundamentals course. And I'm Prashanti SK. I'm a PhD student at IISc and I'll be handling this session. So, for anyone who hasn't been there last week, this is as a quick recap of the session logistics. So, there are 3 such 1 hour sessions that happen every week by different team members, and you'll find timings and Google Meet links on the course announcements page. So, you can pick whichever session is convenient for you in terms of the time and the day and attend that. And the point of these sessions is to focus on problem solving, so that we'll mostly be discussing questions in these sessions, and these questions will be very similar to your assignment problems, so they will likely help you solve those assignments better, but it won't be the exact same question as what's in your assignments. And if you have any doubts from the course content covered in a particular week, you can also bring that up here and I'll try to answer those questions. And please post any questions on chat. And after the session, you'll be getting access to the slides as well as the recording. So you can refer to those in case you have doubts. Okay, I'll just wait a few seconds more since people seem to be joining. Okay, so coming to a quick recap of what was covered in week 2. So, you looked at the various services that the OS offers and different types of user interface like the batch, the GUI, and the command line interface. And also, system calls were discussed in detail, the types of system calls, the transition from user mode to kernel mode, things like that, and then the ways to pass parameters to the OS, the different methods to do that, and then the difference between policy and mechanism, which I'll kind of highlight in a little bit more, and also the structure of the OS. So these today's questions will also focus on these topics. So I would like this to be an interactive session, as I said last week also. So whenever there is a question, if you you can post the answer or the option number on chat, and in case you don't understand my explanation, I will also pause for any questions or doubts that you might have. And why I encourage people to interact is I know how much to explain about things. For instance, if most people get something wrong, then I know that I need to explain that question in a lot of detail because there's something confusing, right? So I would prefer if you guys interacted and posted the answers or whatever you think is the answer on chat. It doesn't matter whether it's right or wrong. So let's start off with the questions. So the first question is, in which of the following user interfaces a task is accomplished by executing a file containing commands and directives? And your options are command line, CLI, or graphics user interface, GUI, batch interface, none of the above. So I'll wait a few seconds to see if you guys have any answers. Please post them on chat. What do you think is the answer to this one? No answers? Okay, let's look at the answer and see if you have any doubts on that. So the answer is batch interface. So if you remember from the last session, these are the three types of interface, right? You have your command line interface, and so I'll try to give examples for each of these, and maybe that will help you understand it better. So your command line interface, if you guys have used any flavor of Linux or some Unix like environment, you would have typed in simple commands like ls or things like that, right? So that is a very good example of the command line interface. And you can also, like this says, you can use some text commands, and you can also have specific options. You can say ls minus l, ls minus al, things like that. So that is the command line interface. And you also have a graphics user interface, which if you've used Windows, and I'm assuming most of you have, and you would have definitely used the GUI, right? So this is where you have this mouse pointer and different apps and a menu, and most of it is through interaction with the user interface, the graphic based user interface. And thirdly, you have the batch interface, which is where you have commands and directives, and you enter these into a file, and then you call this file and execute it. So if you think of this, it's sort of similar to the command line interface, but it's slightly different. So in the command line interface, there is a user, and the user is typing these commands and they get executed. Whereas in a batch file, you typically write these into some kind of a script, and then you just run that, right? So that happens without user interaction, and that's why the term batch interface is used. It comes from that whole batch systems concept. And you might have some operating systems which provide two or all of these variations. For instance, on Windows, you can open up a Windows PowerShell window, which is a CLI version, and use some command to get whatever you want. And similarly, you can also use the GUI. You can double click on an app and open up that app, right? So Windows offers both of these. And you could also, in Linux, you could write all the commands that you want to execute into a shell script and call that shell script. And that is the batch interface. So coming back to this question now, in which of this should be pretty clear. It's just an explanation of what the batch interface does. So any doubts or questions on this? I'll pause for a few seconds. And rather than the answer here, right, what's more important is to think of it from the design of an operating system. So why do you think there are all these different user interfaces? And which would you pick if you were designing an OS? Things like those are interesting questions. Any thoughts, comments, questions, please post on chat. I'll wait for a few seconds and then move on to the next question. Okay, moving on to the next question. Which of the following OS service helps to manage permissions of a file? And your options are IO operation, file system manipulation, communication, program execution. So again, I'll wait for a little bit. Please type whatever you think is the answer into the chat. Doesn't matter whether it's right or wrong. This is a straightforward question again, if you've listened to the last week's lectures. Any answers to this? Okay. Option A, I see. Anything else? Okay, let's look at the answer now. So the right answer for this was file system manipulation, and let's look at these again because that will kind of make it clear. And file system and IO might be kind of similar, right? They are in fact different abstractions of possibly the same thing. But in terms of the OS services itself, if you look at these, the IO operations are actually directly interacting with the IO device, whereas the file system manipulation is taking care of things like permissions. For instance, who is allowed to read a particular file, who is allowed to execute a particular file. And so if, for instance, in Ubuntu or some other flavor of Linux, if you don't have write permissions to a file and you try writing to it, you'll get an error saying read only, right? So a lot of such file system permissions, creation, deletion, management is handled by the OS services for these things. So that's why the answer to this is file system manipulation. And looking at communication and error detection, so communication is for different processes to exchange information between themselves, and these processes may be on the same computer or on different computers, and they might be communicating over a network. So this is kind of a distributed execution. And similarly, the OS has other services for program execution, for error detection. So the answer to this question was file system manipulation. because it specifically asks about permissions of the file and not general IO. So any doubts on this or any content in this? Any questions that you have? I'll wait for a minute to see if there are any questions on this explanation. Okay, let me move on to the next question. So, which of the following OS services helps to provide debugging abilities? And the options to this question are resource allocation, IO operation, communication, error detection. So think about this. We just looked at all of the functions in the previous slide, right? Which service do you think helps with debugging? If you have answers, please post on chat. Is it resource allocation? Is it IO operations? I'll wait a few more seconds. Okay, so the answer is error detection. So let's again take an example for this, right? I think it might be more useful to understand it. So let's say you have a hard disk plugged into your computer, right? And the hard disk stops working. All of a sudden you try to open it and you're not able to use it at all. So which of these functions of the OS would actually help you figure out what is the error? So first of all, the OS has to detect that there is a hardware error, that your hard disk stopped working, and then it might be helpful to you if the OS put that message somewhere. So if you look at this previous slide, right? So that's what it says. The OS needs to be constantly available of possible errors. And these errors can occur in the CPU, in the memory, in IO devices, anywhere. And for each type of error, if there is something that the OS can do to correct it, then it should do that. And if not, it should at least give you enough messages so that you as a user or as a programmer can understand what is going wrong with the system. So if your hard disk, for instance, just stopped working and you didn't have any error message, how would you go figure out what's happening, right? You would have to possibly take apart the hard disk, and then you'd still be puzzled because you would never know what's happening unless you saw some kind of an error message. And this is also done by the OS. So if you're on a Linux based machine, you can try the command DMESG, demessage. And this is a stream where the OS constantly populates a lot of logs, including errors. So if you grep for particular errors, you will see if there's anything going wrong with your system. So this error detection helps us debug when something goes wrong with the hardware, and the OS service helps with this. Any doubts on this? Anything that you would like to know more about this, also feel free to ask. Okay. Let me wait a little bit more before moving to the next question. Okay, so this question says, instead of direct system calls, Dash prefers system calls which is written in Dash, and your options are low level API, low level language, high level API, high level language, low level API, high level language, high level API, low level language. The options are probably a bit confusing here, so I'll wait a little more than usual so that you guys can think about this and come up with an answer. And API stands for Application Programming Interface, by the way. Okay, D, which is high level API, low level language. Okay. So I'll repeat this question again for the benefit of people who just joined. Instead of direct system calls, Dash prefers system calls which is written in Dash. And you have a number of options which are a combination of low and high level API and low and high level language. Is there any other answer other than D that you guys think is right? Okay, let me move to the answer. So the answer is B, high level API, high level language. So let's first think about why this might be the right answer. So for instance, let's say you want to create a new process, right? And at this point, there is a system call which is written in very low level language, which is very close to the operating system. For instance, here the example is NT create process. Now, if when you are writing high level code, let's say you're writing some Java code, if you have to call this system call directly, then you are sort of tied down a lot more to the implementation of it, to the details of it, right? But if you had a higher level call like this, create process, then you need not be bothered about the details of the exact system call. You can just call this, and this internally will take care of passing the right parameters to the underlying low level system call. So which is why high level APIs prefer system calls which are written in high level language. So typically what happens, there is a system call which is actually written in low level language, and these libraries or APIs provide a wrapper around this low level system call, and that becomes a high level system call like create process. And these will work on any system that supports the API. For instance, any system that supports the Windows API, create process will work. So this gives you a higher degree of portability. Just the way if you write Java code, you can run it on any machine that supports a JVM. This is also a similar idea. So the idea here is a form of a high level layer that gives you an abstraction. That means that you don't have to worry about the lower level details, and that's why this is the right answer. Whereas if it was D, so if you were writing something in a high level language and you actually use the low level system call directly, then you might not have as much portability. You would have to actually deal with the details of exactly how this system call is implemented. So that's the answer. So are there still any questions or doubts about this answer and why it's the answer? I'll wait for a bit. And feel free to ask. This is primarily intended to clear any doubts, anything that you don't understand, right? So feel free to ask. There's no such thing as a stupid question. Okay, let's move to the next question. Which of the following parameter passing method has a limit on the number or the length of the parameters being passed? So your options are block method, where parameters are stored in a block in memory, and or stack method, where parameters are pushed onto the stack or popped from the stack. Simplest method, where parameters are directly transferred to registers. None of the above. Any answers to this? So this question is about the three methods of parameter passing that was discussed last week. So which of the methods do you think has a limitation on how many parameters you can pass? Okay, let's look at the answer. So it is C, which is the simplest method where parameters are directly transferred to registers. So, and the reason is pretty straightforward, right? You have a lot fewer registers than as compared to memory. So you might have at most something lesser than 100, or at most a few hundreds of registers, right? So you definitely can't pass a lot of parameters just using registers. But if you use memory or the stack, then that is no longer a concern. So, and this comes from the diagram that was discussed in week 1, right, about the storage hierarchy. So why are registers few in number? Again, it's a design choice that is made based on the chip, right? So the area of the chip is limited, and therefore you can't put a lot of registers there. So you have to restrict the number of registers. Another factor might be the cost of putting registers on the chip in terms of power consumption, in terms of money. So all of that limits how many registers you can put on the chip, and as a consequence, there's also a limitation on how many parameters you can pass using these registers. So whenever you use any of these things in the storage hierarchy, right, be it a register or be it memory or be it any of the cache L1 L2 caches or secondary storage device, you have to always keep in mind what is the size, what is the speed, and that diagram that you saw in the first class, that triangle that showed you the cost, the volatility, the speed, and things like that. That will always that will influence a lot of the design decisions that are made at the OS level. Any doubts on this explanation? Okay, let's move to the next question. Dash allows the OS to run on non-native hardware, and your options are emulation, subsystem, daemon, none of the above. This is a straightforward terminology question, right? So it's a pretty easy one. Any answers? No answers? Is this confusing? Okay, so the right answer to this is emulation. So if you're confused by any of these others, so daemon refers to something like a background process, right, that the kernel runs for some of the OS services. And subsystem more broadly refers to things like the IO subsystem, the memory subsystem, things like that. Whereas emulation is the one that allows the OS to run on non-native hardware. And this might be something that is a lot more interesting to you if you study things like virtual machines and virtualization, where you specifically try and address questions like this. So for instance, you're designing an OS for, let's say, the Intel architecture or the x86 architecture, right? And now you want to run this OS on, let's say, the ARM architecture. So how would you go about doing this? What are things that you need to keep in mind? This is a very interesting thing. For instance, what happens to system calls? So as we saw earlier, to create a new process in the Windows OS, you use this call called create process. Whereas if you're in the Linux world, you would have heard of the call called fork, right? So these system calls are themselves different across OSs. So that is something that comes into play if you're thinking about different OSs. Whereas if you're thinking about different hardware, there are other things that come into play. Like I mentioned, what is the architecture that a particular hardware is using, that a particular hardware is designed upon, and therefore what is the instruction set architecture that is enforced on that hardware. And so if you have an OS designed for some other instruction set architecture, then how do you make it run on this particular hardware, right? Emulation deals with those things. And emulation is a mechanism by which you can actually do this. So any doubts here, any questions? I'll wait for a few seconds. Okay, let's move to the next question. The Unix OS A consists of system programs, B, kernel that contains everything below the system call interface and above the physical hardware, C, provides file system, CPU scheduling, memory management and other OS functionalities, and D, all of the above. So this is kind of asking you about the operating system. So which of the following describes the Unix OS? What do you guys think is the answer? Okay, D, all of the above. Any other answers? Yes, D is the correct answer. If you remember this diagram from the class, right? So you have hardware sitting at the lowest level, things like device controllers, your disks, tapes, memory controllers, physical memory, which is the RAM, and things like that, right? And then there is the kernel, which is all of this. And above that, so the kernel takes care of things like CPU scheduling, page replacement. So a lot of these paging related things you will learn as you learn more about the memory management, virtual memory, things like that. But they are all related to the memory subsystem. And similarly, you have a lot of IO related things like swapping file system, disk and tape drivers, character IO system. All of this is related to IO. And then you have a few other things like signals, terminal handling, terminal drivers, things like that. And so the interface to this is the system call interface, as we learned in the previous week. So your user programs or your applications are at a level higher than the kernel interface. And whenever they want some service from the OS, for instance, they want to access some IO device, they want to write to some file, they want to read from some file, they have to go through this system call interface. So this is the overall structure of the OS. So now going back to this question, so option C is definitely true. It provides services like file system, CPU scheduling, memory management, lots of other things. And again, the OS consists of the kernel, which is everything below the system call and above the hardware, and it consists of system programs. So all of these are true for this question. Any doubts on this? Anything that's not clear? Please ask on chat. Any doubts on this? Okay, let's move to the next question then. So this says an operating system which is divided in multiple modules, A, offers the advantage of not getting affected system-wide when one module is changed. B, comprises the kernel with all the modules. C, provides more flexibility and functionality to each module. D, all of the above. So this is talking about that modular operating system from the week 2 structure of the OS, right? So what do you guys think is the answer? Any answers? Okay, I see D, all of the above. Any other answers that you guys think are right? Okay, let's look at the answer. And yes, the answer is all of the above. And that's because, so think of this, right? Whenever you write code, you would have heard people telling you that code should be modular, right? So why is this so? Because firstly, it's the first option, right? So you're designing an entire system. So if you have this system in the form of pieces, cleanly separated pieces, then when you change the internals of one piece, the other things don't get affected. Because okay, let's see if I can probably draw this out to make better sense. So let's say I have module 1, I have module 2, right? And I have these two modules communicate through a specific interface. And when I say interface, maybe think of it as some particular function call, right? And this function call might take 2-3 parameters. Now let's say I want to change, and there might be multiple such modules, right? M3, M4, blah blah blah, so on. If I want to change something within M1, then I can go ahead and do that as long as I maintain all these connections that go to and from M1. For instance, if M1 is talking to M2 through this function call, I should ensure that that function call remains unchanged. Similarly, if some other module is talking to M1, I should ensure that that remains all right. But other than that, I can go ahead and change the internals of M1 without these other modules getting affected. So that's the first advantage of modular code, and that extends to operating systems as well. And when you have modular operating systems, so the kernel itself is comprised of these different modules. And therefore, as a consequence of this modular design, you also have a lot more flexibility. Like I said, you can change the internals of one module without the other modules getting affected. And similarly, I can add some new functionality to this M1, and none of these others would get affected as long as these interfaces remain the same. Similarly, I can remove some functionality from one particular module as long as the interfaces remain untouched, right? So these are all the advantages of a modular operating system. Therefore, the answer to this is D. Any doubts on this? Okay. Let's move to the next one then. Memory management activity does not involve A. Keeping track of which part of the memory is currently in use and by whom. B. Deciding which processes and data to move into and out of memory. C. Suspending and resuming processes. D. Allocating and deallocating memory space as needed. So this is about memory management, and which of the following does it not involve, or which of these activities do you think is not at all related to memory management? Any answers? Okay, C. I see one answer on chat. Any other possible answers? Okay, so C is the right answer, and it's kind of obvious from these options, right? This is about processes, as in when do you suspend a process, when do you resume a process, and that's not related to memory management. Whereas things like keeping track of who is using memory. So for instance, if you're on a Windows machine, right? Many times you'll say, oh, my system is slow, maybe I'm low on RAM. And then you open up Task Manager and you look at the RAM. Let's say you have 8 GB of RAM. So Task Manager shows you a list of applications and it says this application is using say 1 GB, and then you say, okay, this is why my system is slow, and you kill that application, right? Similarly, people do use the utilities like top on Linux to see which processes are using memory, and this kind of tracking is done by the OS as part of its memory management. Similarly, which processes and data to move in and out of memory is also handled by the OS. So for instance, if your application is requesting for a particular data set, the OS has to move it from storage to memory. And similarly, if something is no longer used, it might decide to move it back to storage, right? So this is also part of memory management. But C, which is completely about processes, is not about memory management. And again, allocating and deallocating memory space is part of memory management. So is this explanation clear, or any further doubts on this? Okay, so before going to this question, I'll just take a quick couple of minutes to check if you guys have any doubts with the week 2 content, right? If you do, I'll take a few minutes to answer those questions before moving on with these, because we have 15 minutes left. So if you have any questions, any doubts, anything that is not clear with week 2 contents, please feel free to ask now. No questions? Anything from week 1? Anything that's covered so far that's kind of not clear or confusing or needs more explanation? Anything like that? Okay, I'm assuming there's nothing. So we still have a few more minutes. So if you remember some questions, please post it on chat. You need clarification on something, or you can even ask next week in the same session. That's perfectly fine. But if you do have any questions, please bring them up during this session, because this is intended for clarification of doubts. There's also the discussion forum where you can post a question and someone will answer it. But yeah, that's up to you. Okay, moving on to the next question. Which of the following is not a task of file system management? And the options are: backup files onto stable storage media, optimizing and deciding which file data is to be stored in memory, primitives to manipulate files and directories, mapping files onto secondary storage. So think about this. This one might be slightly more confusing than the previous one. But think about this. Is one of these not related to file system management? Which do you think it is? Okay. B, optimizing and deciding which file data is to be stored in memory. Any other answers? Okay, let's look at the answer. That is correct. B is the right answer. Although it talks about which file data is to be stored in memory, the focus here is about memory. It's about managing the memory and what gets stored there, right? So B is part of memory management. Whereas things like C, primitives to manipulate files and directories, mapping files onto secondary storage, backing up files, all of these come as part of storage management. It's not a part of memory management, storage or file system management, right? So B is the option that does not belong to file system management or is not related. So that's the answer for this. Any doubts on this? Okay, Let's move to the next question then. So, operating systems are typically written in A. Assembly language, B. C language, C. C++ and other scripting languages, things like Python, Perl, D. All of the above. So, which do you think it is? So, a typical operating system, what do you think it would be written in? And things to keep in mind while answering this question are, why would you write it in a particular language? For instance, if you tell me you'd write it in C, why would you write it in C? Or if you'd write it in assembly, why would you do that, choose to do that? And what are some of the consequences of that? Any answers to this question? Which language do you think operating systems are typically written in? Okay. D, mix of languages or all of the above. Okay. Any other answers? Nothing else? Okay, let's then move to the answer. So, D, all of the above, and I think this was discussed in the lecture as well. So, why all of the above? So, assembly languages for performance, right? Because assembly is what is closest to the hardware. When you write assembly, that's actually going to be executed, right? So, it's very good for performance. But why we don't write everything in assembly is it becomes very hard to write. Second thing is it's not very portable. So if I write code on one particular machine, then I can't easily port that assembly code to another machine, right? So even though you have assembly being used for performance, the entire OS is not written in assembly, because then it would become very difficult to port it, right? So these other languages like C++, C and scripting languages are used are all more high level as compared to assembly. So these are written so that your OS isn't very closely tied to hardware. Of course, the trade-off then is that you don't get as high performance with these things, but that's kind of an accepted thing because it's giving you portability, right? But the critical parts like maybe some IO operations and things like that are all written in assembly so that you get performance from those. So the right answer to this is all of the above. So any doubts in this question or any clarifications that you want? Okay. I think we have one last question. So, which of the following are examples of abstractions? And your options are processes, files, interrupts, both A and B. So, which of these do you think are abstractions? Any thoughts? So this was probably not directly covered as part of the course content, but it's sort of an important concept, so it helps to think about it. Okay, let's look at the answer. So the answer is both A and B, both processes and files, and I'll take a little time to explain this, right? It's an interesting concept. So here's a table that I have for this. So if you take compute as the resource, basically your CPU in this case, at the lower level you refer to them as processor cores or as CPUs. But at the user level, the abstraction that is presented is in the form of processes, and later on you'll also be studying threads, right? So these are the two abstractions that are presented, and this actually represents something running on the processor core. Similarly, if you think about storage at the hardware level or slightly above that, we talk about hard disk blocks, things like blocks, sectors, right? These are things that actually exist on the device. Whereas if you look at a much higher level, what is presented to the user is always files, right? So if you click on your hard disk and you open up a GUI window, whatever you use, right, File Explorer or something else, you see a bunch of files. But what actually exists on the hardware, it's blocks and sectors, and going further one level down, it's all bits, it's all zeros and ones, right? So these are just abstractions that are presented at a higher level, and the OS is sort of doing this for ease of use. So for instance, if data were to be presented as a sequence of bits, right, none of us could understand it. And that's why we kind of have this convenient representation of files, of processes, of threads. But remembering that there are multiple levels along the stack, that you have many of these abstractions and what they actually represent at the hardware level, that's useful. Similarly, if you've done a bit of networking or C programming, you would have heard of sockets, right? If you look at a lower level, the same thing is referred to as a ring buffer. And similarly, you would have heard of IPC, interprocess communication. At a lower level, it resolves down to IPI. So these are all some abstractions that different layers provide you, and that's building on top of what the hardware has to offer. So this is something I felt would be useful. And the last thing I'll cover today is this, the difference between policy and mechanism. This is also something important to remember throughout the course of learning operating systems, and in general learning any other thing about design, right? A policy is talking about what you will do. For instance, your policy might be first come, first serve. You might say, like say for a scheduling algorithm, right? You say whichever process comes first, I'm going to schedule that first. Now the implementation talks about how you're going to do this. So for instance, I might have a queue and I might use that queue to schedule processes, and that's an implementation of this policy. And why we keep this separate is because again it gives a lot of flexibility. So let's say I change the policy from FCFS to something else, right? I can still have a queue-based implementation. It doesn't matter. As long as that queue-based implementation can cater to this newer policy, it's fine, right? So this is again what enables you to make these design choices very flexible, right? For instance, if I were to give a very simple example, not even of things like scheduling. So I might say something like, as a security company, I'll say that every employee who enters should be authenticated. That is the policy. Now the implementation of that might be giving everybody a key to unlock a door, or I can give people RFID cards that they scan somewhere, right? And these implementations are left to whoever is actually taking care of that. Now, if I were to change the policy to something else, I can still have the same implementation. Suppose now I say that only certain people are allowed access to this building, right? I can still have people using the same keys, but I can withdraw those keys from some people who are not allowed into the building. So the implementation and policy are kind of separate, and this allows for maximum flexibility. So this is an important concept, and with that I come to the end of my slides. And last session someone asked me about reference textbooks, so I've added this here. So typically at an undergrad level, both of these, Tannenbaum and Silver, Schatz and Galvin are recommended. So you can use either of these. I also recommend this operating systems 3 easy pieces, which is linked in these slides. You can go click on that and the textbook is available. This is also a great book to use. So if you have any questions, I will wait for another 30 seconds. If you also have feedback about this session, something else that you want me to cover next time or do differently, please post that in the chat. If you don't have anything, I'll be ending this meeting in about a minute. Thank you so much for taking the time to join this, and thank you for participating in the questions and answering them interactively. Any feedback for me, please leave it in chat. Okay, there's one question. What is portability for languages? Right. So portability usually refers to being able to write in one place and being able to execute it in other places. Basically, if I write a program, it shouldn't be tied to the machine, right? It should be portable, as in I can take that same program and run it anywhere. But there are some constraints to doing this, right? For instance, you would have seen, if you take a C program, you compile it and then you execute it. So if you have to run this C program anywhere else, you might have to compile it again. You can't take the executable and run it, right? So there are different degrees of this portability that come into play, but portability broadly refers to the ability of being able to write it once and execute it across a variety of hardware or platforms. Is that clear? Does that help? Okay, great. So thank you for keeping it interactive, and I hope you learned something from this session. So see you guys next week. That's all that I had. So thank you.